Welcome back. My name's Andrew from GP3D, and you have found us in part 3 of our beginner blender series for 3D printing. So, a quick recap: in the part 2, we finished off building the model and exported it to the STL file format. So now we're going to use that file that we created, bring it into our slicer and do all of the manipulation configuration so that it's set up ready for printing. So let's get stuck straight into that. Okay, so this is Prusa Slicer. So there's heaps of different slicers available on the market. I use the Prusa printers for all of my printing. No real reason other than that's what I decided to get when I first started. And they've done the job for me. Very straightforward, not too many issues, easy to maintain. They do what they say on the cover, which is print objects, and that's what I wanted it as an appliance. My hobby is not tinkering with the printer itself and modding it and enhancing it and debugging it, all those sort of things. So lots of people out there love to do that sort of hobby. But for my hobby, the printer is literally an appliance which I want it to just work. So that's what I went for initially, about 5 years ago now, I think. Well, just over, almost 6. So yeah, that's what I went for. So the two probably main printers on the market, or brands on the market at the moment for consumers like us, is the Prusa and the Bamboo. So there's a bunch of others, Crealities and other ones which have all different models and have different price points and levels of robustness and quality and consistency. But the two that I guess the easiest to learn and just work, so you don't have to be a super guru at debugging and fixing printers, is Prusa and Bamboo. So I've got no experience in anything other than Prusa and Prusa Slicer, so I'm not the right person to ask for evaluations of comparisons. But I can just tell you what I've done and do, or what I've got. So yeah, don't take it as a recommendation of one over the other. It's just one type, and that's what I use. Yeah, so this is the Prusa Slicer, and the default view, you get your sort of another the 3D viewport, very similar to Blender in that way, that you can move around. And then you've got a whole bunch of settings. So you've got your plater here with all of its settings, print settings, filaments, printers as well. So the first step we want to do is add an object. So we click on the add here, and we go to, just so in the background, I will go and open the STL file that we just exported from CAD. There we go. So there it is. So magic. So it comes into, it'll come in here just orientated the same as the way I designed it, which doesn't mean it's the way it should be printed or the way I want to print it, but it'll literally import in the same orientation as the way that it was exported from the CAD model. So we can see here, it looks pretty good. If it was a bit of a broken mesh, like non-manifold, there's a really cool feature which fixes 99% of the cases. Well, let's go 95% of the cases. Fixes the vast majority of cases automatically. So you can right-click on the object and go fix by Windows repair algorithm. I think pretty much all slicers would have the equivalent of this. And it goes through a repair. So when you bring it in, if you've got a little icon next to the name here, I can't remember the icon. I think it's like an exclamation mark or a warning, like a warning triangle exclamation, something like that. If you just click on it or right-click fix, it'll do this little fixing process and fix up your mesh, which is really cool. If that doesn't fix it, then you've got to go back to CAD and work out the problem, like what we saw with the cylinders before. If it's too far broken, it might not be able to fix it properly. Or it might fix it, but not not actually structurally correct for what you're trying to design. So keep that in mind. With a Prusa slicer, there's most slicers, but with this one, there's all of the pre-loaded configuration profiles. So depending on what layer height you want to print at, like 0.1, 0.15, 0.2, there's a whole bunch of preset profiles. Filaments you can activate or basically install or activate any number of different predefined or presets for all of the different companies' filaments. So Prusa One has all of their own products, of course, plus it has a whole bunch of other brands. Not everything in existence, but a lot. So for this type of, a lot of what I print is Prusa PC blend. So I would select that. And then the printer is, whatever your actual printer is. So when you install the slicer, you would activate the printers that you have as printer profiles that you want to have available. So you can see here I've got the older ones that when I first started I had the Mark III and then the Mark III's upgrade, and then since then the Mark IV came out and the Mark IV's. I've only got the Mark IV. I didn't do the S upgrade. Didn't really have a benefit for this type of purpose. But yeah, currently now looking forward to the new Core 1, which is now out. So I'm hoping to be able to get one of those in the near future. And that'll be very interesting with the multi-material add-on as well that they're going to release. Index, I think, INDX, is another company that's collaborated with Prusa, and they are producing I think it's up to 8 heads, so 8 separate head adaptation that you can upgrade your standard Core 1 to have that feature, and then you can run multi-material. So you can have obviously different colors of the same material and different materials. And I'm pretty keen to finally get a printer with different materials so that I can play around with different materials for the support structure. So with the support structure, it has to have a very minor separation from the main component so that it can break away after it's printed, which means that it supports it as it prints and it can be removed later. But the downside of that is that the underside surface of your component usually is pretty ugly. It's not smooth. It's not sort of pressed because, the plastic can't be pressed onto the support hard because that way it'll stick and you'll never get the support off, so it defeats the purpose. But if you can use a different material that is effectively not compatible with the material that you're actually printing with, i.e. It won't stick to it. You can press them against each other and they don't stick, which is the perfect scenario for supports. So you can have like a 0mm interface, but then the support still breaks away with a different material. So I'm super keen to have that in the future, which will be a good step forward. So basically, it doesn't change the strength or the usage of the component, but it does make it look a lot nicer. So the cosmetics of that underside, depending on how it prints, would be heaps better. So, for example, I probably might print it this way. So for this component, now we've got to decide, how to print it. So it's a good segue. Every component would be kind of different in terms of how you decide to print it, like the angle you print it at and the settings that you need to print it with. So you've got stuff like, this orientation. So you can see there I've just tilted it up at 45 degrees. So I'll undo that. So what you could print it like this, and I'll click on slice. So what slice does is what the whole purpose, or pretty much the whole purpose of this software, the slicer. What this does is it slices it horizontally into many layers. So we've set our 0.2 millimeter structure, or 0.2 layer height, which is pretty standard default. A smaller resolution, like a 0.15 or a 0.1, is a smaller resolution, and it usually gives a nicer finish. Like the layer lines are less conspicuous. It's probably debatable, but I think I've found that a 0.2 gives a slightly better adhesion, so each layer adheres to the previous layer better, which results in a stronger component. So for most components, it's either 0.15 or 0.2 I print at. I think they're pretty similar. 0.2s, I would say, is the ideal as an arbitrary, non-scientific valuation. The 0.15 gives you maybe a slightly nicer finish, where you don't see the layer lines as easy. And the 0.1 is the same thing again, maybe not quite as good adhesion, so it might compromise the strength of the component, but it'll look nicer on the surfaces. So what you can see here is a few cool things. So I've done the slicing, and we've got this slider here on the right. So if I slide this down, you'll actually see it at all these different layers of the object, which is like pretty awesome. I'll change the number of perimeters here to 3. And go back, because this will sort of demonstrate the layers a lot better. So right down the bottom, that's your first layer. And then this slider across the bottom here will actually show you the nozzle as it goes through that layer. So you can see the sequence that it's actually going to build the part, which is mega cool. How awesome is that? And then you can see here on the left, it's giving you like a preview of the G code. So the output of this slicer is going to be a file called .g code, or in this case, it's binary G code, so BG code now. And that is the output that the printer understands. So that sort of continues our process. The output of this slicing operation is BG code. I'll call it G code. And then that G code file is what gets transferred to the printer, and all this sequential instructions of coordinates and temperatures and movements is what the printer is going to execute for us, which is kind of sort of very simple when you break it down into its granular pieces, but kind of very complex at the same time, with all of these millions of little pieces working together. So it's pretty incredible. Yeah, so this slicer is very cool software, and it shows you how everything's going to be printed effectively, step by step. So each one of these lines on the left here, like you can see they're numbered, is basically one step for the printer. So it'll be maybe one movement of the print nozzle, like an X coordinate, a Y coordinate. It'll be a sort of a temperature setting or some other retraction type setting, whole bunch of different operations that the printer can do, and it's just telling it to do those things sort of one set of operations at a time. You can see, even if you look at it, you can see like a code like G1, and then a coordinate like X coordinate and a Y coordinate, and an E coordinate, which is the print head extruding, so E for extruding the filament down. So it's saying how much filament needs to be pushed out. So it's just a whole massive sequence of all these different instruction types. Cool. So we can see how this thing's going to be built. And then we've got a whole bunch of settings. So print settings, layers and perimeters. So you've got your layer heights, number of perimeters. Is something I'll definitely like. If you're just printing a basic static model for the shelf, two perimeters is usually enough, and you'd probably be using a material that's not designed for high impacts. PLA, PETG is a nice material for static models. Some of them, like the tough versions or some PETGs, could be used for RC racing cars or other similar models, but they definitely will break easier, and they tend to not hold threads very well. So if you're screwing a bolt into them, it'll cut the thread the first time and hold pretty well. But if you're taking it out, screwing it back in, it wears out the thread very quickly. PETG and PLA are also quite stiff, so that makes them a bit brittle. PETG is a little bit better, has a little bit more give than PLA, for example, but is still not that flexible in terms of material properties compared to the PC blend. So that PC blend material has pretty much made everything I've done possible. Like all of the suspension components, everything that's going to be, take force, take impacts, needs to be assembled, disassembled many times, like all the threads, to be, to maintain their integrity. That material has just worked amazing for me. So pretty much all my kits, all my cars have been done with that, especially the off-road buggies, for example. So it's pretty awesome. There's definitely better materials in the world. Most of them would be far more expensive and maybe not as accessible. A lot of them require a whole different printing technology. But for myself, for the consumer, with a consumer FDM type machine, at a reasonable price point, it's much. PC Blend is probably twice at least more expensive than the PETG, 2 to 3 times. But that equates to a few cents or a few dollars per component. So it might be like $1 instead of 40 cents per component, depending on how much material a component uses. So it's when you break it down, it's a small incremental cost per piece, but it is definitely more expensive than some other materials. But it makes it viable. So it's a perfect combination of availability and strength and performance and impact resistance and flexibility and price, which is awesome. So perimeters, let's just bump it down to 3. We've got infill settings. You can get all sorts of different effects, gives different weights to the component, different looks and different effects on the outer surfaces as well for some of the settings. Just as a general starting point, I quite like the rectilinear infill, mainly for the reason of it's quite light. There are lighter ones. There's literally one called Lightning, which I think it both looks like a lightning bolt and also physically uses less material. It's very, very sparse, and it only puts a little bit of sort of lightning. It looks like lightning in the slicer. It only uses very minimal amount of material to achieve the support it needs for the top surfaces. But of course, it won't have the strength. So for structural parts, strength parts, I found rectilinear is pretty good. It's got a good combination of strength and lightness. And then concentric I quite like for the top and bottom fill patterns, depending on the component. Sometimes when you orientate the components, there's basically no top and bottom fill, or it's so minimal that you don't really see it anyway. It's just at the corner of the component. So, but if there is a top surface, I quite like that. It's sort of symmetrical and looks a bit nicer. You can do ironing. I won't get into that today. That pretty much just smooths out the top surface or top surfaces, but we'll leave that for now. So infill, how dense the infill is a key number. You can change it to almost anything, but I've generally found if I want a solid object, I just increase the perimeters. If I want it slightly stronger, I might bump that to 20-25%. If I want it slightly lighter and it doesn't need the critical strength, then you can drop it down to 10.5, and you can type in any number you want. So I could type 7. It doesn't have to be a whole number that they've got in the drop down. But 15 is the standard, I guess, default. And once you change all of these settings, you can instantly see the result. So you can see here we've got 3 perimeters, like 1, 2, 3. And if I slice it again and scroll down our layers a bit, so you can see the infill now. Because I've only got three walls, so you've got 3 walls there, 3 walls there, and then you've got the middle bit, which is the infill. And this is the rectilinear pattern, so basically a square rectangle type pattern in a sort of box structure, I guess, which I find makes it adds good strength and minimizes the weight gain of the part. So if I want to make this part stronger, I'd probably ignore the infill, and I would go and increase the perimeters. So let's see that. Whoops. Let's see the effect of increasing it. So from 3, I'll bump it up to say 6. So if I go back to the plater, see it's gone away from the sliced view because I've changed the setting, so it has to reslice. So we just click the slice button again. Yeah, so now you can see we're halfway through the object here. Now you can see that because we've got 6 sidewall, we've got 6 perimeters. So the orange is the outside perimeter, and then we've got 5 more inner perimeters, or inner walls, I guess. You've got 1 perimeter and then 5 internal walls. And they, in some areas of this part, that's enough walls to actually touch. It meets up with the other side, so you get effectively a solid component. But you can see in some areas where it's a bit thicker, the 5 or the 6 perimeters don't fill the entire space, and then your infill takes effect. So you can see it up here a bit better. So there's still a bit of infill here, but you might go, oh, that looks pretty nice. I'll leave it like that. It's got enough, quite a lot of perimeters around the holes, so I'm going to get good support there, because that's where you need a bit of strength as well. So you could go, yeah, that looks nice. Or for such a small component and for such a minimal difference in weight, I might go, stuff it. I'll just increase the perimeters heaps so that effectively it just fills up the whole lot. So slice it again, and you can see here there's no infill now. It's just got perimeters all the way in until they meet in every part of the component. And that gives you the solid, basically a solid plastic object. For this object, it probably needs it. With this PC blend material, the material shrinks slightly as it cools. So as it prints, super hot, like 275 degrees, and as it cools, it'll shrink a fraction. And that shrinkage is an issue with 3D printing, which is because as each layer prints on top and starts shrinking, it's very, it's like 0.0 something of a millimeter, but you just get that tiny amount of shrinking at each layer, and because the layers are stuck to each other, they can't sort of pull inwards. The forces tend to pull upwards on the edges, so the edges of the component try to pull themselves off the print bed, which is the key issue printing materials that have that shrinking characteristic. So what you can do, there's a whole bunch of things, but like a chamber, you print inside the chamber. So you can see here, maybe see here behind me. You can in the other view. We'll go to the, see here. I've got, where is it? This one, little box. Yeah, so a chamber around the printer keeps the temperature higher and lets it shrink at a slower rate. So it sort of helps reduce or minimize the tendency for it to lift off the print bed, because once the print sort of detaches itself from the print bed, it's pretty much ruined. You might get away with it sometimes if it's only a tiny bit and it's later in the print, but you'll find that it'll, the corner will lift up, the printing above it will get a little bit sort of squashed and messy, like not the proper shape that you want the component to be. So if you're wanting accurate engineering components, it's critical to keep it down. So one of the methods of doing that is adding a brim. So you check the brim box and reslice, and now you can see it's the green is the brim. So it'll print this brim as like a extra material to give it adhesion. And because the brim is only one layer, you can see here, you just get one layer. There aren't layers on top of it to then try and pull it up or lift it up as it shrinks. So that stays nicely stuck to the bed, and you get the interface between the brim, that inner line of the brim and that edge of the component, so that sticks together. So then it's basically stuck to your component. It's part of it initially, and that helps keeps the whole thing flat and structurally accurate as you desire it. And then after it's printed and it cools down, and you break it off the print bed, and then this very thin, it's only 0.2 millimeters because that's our first layer, or all of our layers in this case, but first layer is 0.2. It's a very thin bit of plastic, and it generally just sort of, you can rip it off or you can slice it off, and then you just clean up the edges with the scalpel and sandpaper. So that's another good method that I often use, especially with a small component like this. You might get away with it or you might not. A smaller component you can get away with usually. It depends on your printer and your environment and the moisture and how clean your bed is, and what sort of preparation you do. So there's a myriad of items that I'm not going to go through in this video for another day. And all those sort of things affect whether it prints properly and stays stuck to the bed. Even the bed material, like the actual type of print plate that you use, steel and PEI and various other texture and non-textured other materials. You can put glue on it, all sorts of stuff. But yeah, the idea is to keep it nicely stuck to the bed. So all of those aspects combine to keep it well stuck. Yeah, so I could print it like this. It'll print nice and flat. You got a nice sort of shape of the thing. You get good flat surfaces. It'll be very strong around these holes because all the layers, the layers go up, perfectly around the holes. It'll give you good strength for the threads to cut into and to support what it's supporting, the shocks in this case. Oh, I noticed a hole missing. I'll get back to that. So those holes are good, but you come down here and you see this hole. So this one is actually a problem. So what you'll see, or one aspect is, because you're not actually printing a sort of circle here, you're just printing flat layers, you tend to get an elongated hole. So this will end up a bit wider than it is tall, which usually isn't a major issue because you're just threading an like a 440 or an M3 or whatever bolt into it, and it just cuts the thread and you're fine. So that's less of an issue. But what we do have, what you can see here is, I'll come down a bit more. So what you can see is that we've got this very small layer area in all of these sort of layers around the outside of the hole here. So this will basically be a weak point in the structure, and it's where it's going to break. So it doesn't matter how strong the rest of it is. Yeah, you've got really super strong points, but then you've got this super weak point, and nothing else is going to break, but this bit's going to break. So if you get an impact or a force, whatever, it's going to split here very easily on one of these points, and then you're stuffed. So what we want to manufacture is to more evenly distribute the strength. So I might need to sacrifice some super strong parts or some cosmetically beautiful parts or areas of the component, and I want to distribute the strength so it's more average, more even across the whole part. So we're basically lifting up the weak point. We might need to lose a little bit of strength in the most strong point, but that's a balance that's going to be fine because if it breaks somewhere, it doesn't matter how strong the strong point is. And generally, if you can make your weakest point strong enough, anything stronger than that's going to be better again. So it doesn't matter that it's 90%, not 100% strong. Yeah, so for this component, what I will do is go back to so this is the slicer view, which is this icon, and then the one to the left is the editor view. So I think tab will toggle between them, so pressing the tab key, or you can just click on these icons. So yeah, we'll go back to the editor view, and I'll do two things. First is, I noticed I've missed a hole. So my component has a hole in the top, which you probably can't, oh yeah, you can see, there you go. Little tiny hole in the top, which is actually, I think, where the top shock mounts for the pod. And I have probably forgotten it. So this is a good demonstration of the iterative process. I will toggle back to Blender and go, yep, I have missed it. So very easy. We go, right, I've got it was hiding around the side there. So I've got the cat out here and give the same treatment to it, change that to wire. And then, so shock mount, yep, I've missed it here. Yeah, so now I want to go Q and B. I'm going to add another boolean, and I'm going to make it that one, center top, fast, copy, very good. And I'm going to demonstrate something here as well. So see how this is now sequentially after the mirror. And in this position, in this object, it would actually work either way. So I could drag this above the mirror, and you can see that it's pretty much doing the same job, making a hole. But I'll grab this and move it 5 millimeters. So we'll put this back, but just say that was the design. And I go back to here and add my boolean below the mirror. See how, because effectively the mirror has happened first. So if my mirror is about to happen, yep, there we go. So if my mirror is about to happen, so my object looks like this, my hole doesn't exist yet because I haven't executed it. So remember, this is executes in sequence, top to bottom. So if I then execute the mirror, I get my object here, and then I execute my boolean, which happens afterwards. This is my boolean operator object, and it chops out a hole here, and that's it. But just say I want, there should be a hole in both sides, if that was the design. I want to move that to above the mirror. So basically I come down here, I execute that hole, and then I execute the mirror. So that's what Blender's doing in terms of processing sequence. So then I would have my hole on both sides. Because this is in the middle, it kind of doesn't matter, but I found best practice is just to do it the same way. So you'd put this before the mirror. So effectively, it's just chopping out that hole there in our object as it currently stands, which is half the final result, which is what we want. And then we just mirror it. So execute the mirror, and our final result is a hole in the middle. So yeah, so it's really super easy, like doing this non-destructive type Boolean modeling. Super easy to make those sort of changes, fixes, evolution of your component. So yeah, now I've done that, I just go and export it again. And if I flip over to the slicer view, all I need to do now, because I've already imported this object, it's the same, it's basically pointing to that same file. So all I need to do is refresh. So I can hit F5. F5 will refresh all the objects in the slicer. I've only got one open now, one imported now, but F5 does that. I can also right click on a specific object and go reload from disk. And you'll see now I've reloaded my model and it reflects the fix I did, which was to add the hole in there. And that's that process. Awesome. Cool. So that was the first thing. So second thing now is I want to try and improve my strength here. As I sort of mentioned way back at the start of the videos, I will probably change the design of this area a bit, like add a bit more material. I might put a step sticking out with a nut on top, so you could secure it with a nut as well, potentially. I'd look at the car, it might be able to extend out a bit further if it doesn't hit anything. Just increase the shape of the component to add more material, which will make it stronger. It might be strong enough as it is, might not be. That's the evolution process of designing, estimating how strong parts need to be, but then you ultimately have to go test them and see if they break or not. Not scientific, but that's the way I do it. And after a while, you obviously get a pretty good feel of what works, what doesn't, how much material you need in certain circumstances to make a component fit for purpose and strong enough. But initially, it's just gut feel and trial and error and physical testing. Yeah, so what I'll just say this object as it is. What I would do is probably rotate it. So I'll tip it up at 45 degrees. So 45 degrees is a super cool number in printing, because what that does is it means that you don't really need much support, or maybe no support in a lot of cases, because printing layers upon layers at a 45 degree overhang will effectively work. Like, you can't print in midair because there's the gravity will just the molten plastic will just fall in midair, so you can't print onto nothing. But what you're printing onto is the previous layer, and a 45 degree angle gives you enough non-overlap, I guess. Some of the next layer of print will be off the edge and some of it will be on the previous layer, so you've got enough on the previous layer that it sits properly, prints nicely, and you get the perfect result. So 45 degrees is a very important angle. Cool. So now this has done a number of things. One is I'll do a quick slice. So we can see there's actually no top and bottom surface now. So this one line is our bottom surface effectively, which is negligible. And the top surface, there is no top surface, but the very top of the print is this one line here. So the top layer, if we go down one layer, if you can even see that, you can see that it's like one little layer. Go down a few more. So effectively we've removed the top and bottom layers. Everything is pretty much a side, like sort of a sidewall, which also gives you a nice consistent texture. So 3D printing, you obviously have all of the layer lines, but you get that evenly across the whole object rather than layers on the side. The print bed, the smooth print bed or the textured print bed surface at the bottom, and a top layer which looks, you can see all the lines where it fills in the top layer, and generally it's not consistent texture. It never looks fantastic. Looks as a secondary purpose here, but it is quite important. I like to try and make it look as nice as I can as well. So yes, that's one thing it's done. The second thing it's done is the cross section around the holes will be bigger. So up here it's all good. It will be probably even better than it was before, because you've got a lot more surface area. But effectively, it'll be good both ways there. But if we go down to this problem area, So this is the sort of bottom of the actual component where it goes in the car, and the bolt will go up through the carbon plate and try and thread into here. So what we've done here, it's the best way to show this. Yeah, so at any point around the hole, like sort of here, or even further down, we've got, you know, a lot of surface area, like big massive surface area. And then as it goes up and it encapsulates the full perimeter of the hole, we've still got like a lot of surface area around. We've still got narrow edges, of course, because that's where the hole is, and that's where, you know, you'd redesign the actual shape of the component if that was not sufficient. But what we have done just by orientating it as it is, we've increased a lot of the surface area here. So there's no, you know, it's not as small as the previous version would give us in terms of the weakest point. So we've basically bumped up the weakest point massively, and that could well be strong enough. Might not be, but that's the testing step after that, or decision to add a bit more material, because it slants in. I could easily make this more of a square shape, of course, and go up a certain amount and then come in. So that's the, you know, design revision process. Yeah, so as it is, that's pretty good. It might be sufficient. And then the third thing it's done is made this print very unstable. So now we've only got this one skinny line, which is the first layer. So if I go right down to the first layer, so we're anchoring this whole print on just this one thin line, which might come detached, like it might warp, it might not be strong enough, the whole part might wobble as it prints, you know, a little bit of vibration, so you might get very bad print quality, and all the sides will be terrible if it vibrates too much. It might simply just break off, you know, if it gets slightly knocked by a bit of extra material as it prints, if there's a over extrusion or a bit of debris. You know, if the print head just sort of puts a bit more force into the object as it prints, it can just literally break it off the bed and your print's dead. You have to start again. So there's a couple of ways we can address this. For this one, the main and maybe the only thing we need to do is, I'll just toggle back to edit view, is what I can do is I can actually sink this component sort of into the bed. And obviously it won't print anything below the bed because it's a physical thing, but we can see here the Z height of where this object's sitting, so it's center of the object is probably up here somewhere, wherever we designed it. But if I drop this down, so I can drop it down numerically or using the interface, but we go from 17.8 to about 17. So now you can see this is actually dropped, like it's called sinking. Oh, yeah, sinking. So I've actually sunk the object into the bed, which effectively chops off that piece of the object, so it never gets printed. Will only get printed from the bed upwards. So now if we slice, you can see here we've got, instead of just one line, we've got 3 lines. So I've got like a bigger surface area for it to contact. And that may or may not be enough without support, or we can add support as well. So we could keep going. Another way to do this is like select the object, you can click the move icon and grab its handle. So see here, I can move it up and down, sort of freeform. So if I go, I'm sacrificing a portion of the object, which may or may not matter. In this case, it probably won't matter too much because it mounts by these 2 bolts. I've still got quite a bit of surface area for it to sit flat onto the carbon plate it attaches to. And so basically just trying to find a good compromise of increasing that surface area as much as possible without cutting off too much of the component. So I could change that to say 17, 16, yeah. So that's probably pretty good. So it chops off the corner a bit. 7.8 still leaves enough surface, so it's, when you bolt it down, it sits flat and it won't wobble or break or whatever because of that. So that gives us a better adhesion to the bed. And then the next thing to look at is supports. So at the moment I've got supports is none, which is set here. And I can also look up here, see these blue parts, that indicates an overhang. So that's where it's actually going to print, in this case, a very small amount of material over thin air. So it's basically, there's no plastic below that when it prints it. So it's going to print it into thin air, which means for that little bit, it's kind of going to sag a bit. So it might sag away from where it ideally should be. And that'll give you just a rough spot on the print. You lose a bit of material. It's ugly. If it was really bad, you would compromise its shape and strength. Tiny bits like this probably won't matter too much. You'd just trim it, sand it with a bit of sandpaper. It's so minor. It'll be so minor it probably wouldn't matter. And these ones at the top of the holes definitely won't matter. But what you can do is enable supports. So firstly, I'll enable support on build plate only. So that's that setting there. And then reslice. So now you can see it's basically an automatic determination that's made based on all of its settings, which we can manipulate. And it's put up these bits of supports, which are probably not really going to help much, based on my experience and gut feel. So I would probably just print it like this. The other option we can do is I can do paint on supports. So it's kind of like an override saying I want more supporting capability, or a more comprehensive support at certain areas. So I can go into this mode, which is the L key, and it gives me into this paint on supports. And I can say I want some more supports in these areas. And these holes, I probably would leave it normally, but I can right click and actually put a red mark, which is a blocker. So that's going to block supports from the top of those little holes because it's so minor it's irrelevant. So it just wastes a bit of time and material in the print. But the key areas is there, which is an overhang. I could add a bit more support down the bottom if I felt it was necessary, like sort of, put it along all this area to just give it a bit of stability, but I don't think it really needs it. So yeah, let's see what that looks like though. So that's my paint on support. So I'll slice again. So now we should be able to see a few things. So see all this dark green interface. So that has given me some extra interface material, is dark green, over, making sure it supports this bit of blue, which is the overhang, as best as possible. So it's only that tiny little bit. So as I said, it probably would be sanded off, no problem. And it would save you all of the extra material and time for the print to do this. But that's a decision of sort of quality, necessity versus time and material. It's probably only a few cents of material and 5 or 10 minutes of print time. But on a small object like this, it's irrelevant. On a bigger object, it could make a big difference to your material usage and your cost, and your time cost. Yeah, you can see it also here along the bottom, because I painted that bit. It gives a bit of support at the bottom here, just to give it a bit of security, to keep it balanced, or keep it supported as it's building the foundation here, because then it's going to cantilever all of this extra print until it gets further up. So it helps support it, because you've got extra weight as it prints. You don't want it to get too heavy and fall over. Again, a small object like this would be fine, but a big object could actually physically get too heavy for its, stiction at the base, and it could break off the bed just due to the weight and nothing else. Another little setting that's pretty useful around the supports is the distance. So if I go to the print settings and support material, there's a style, and there's also this top contact Z distance, or Z distance if you're in the US. So you can change this to any number. The default's usually 0.2. So that's the gap between the support and the bottom of your actual component. So that lets it detach when you finish, which is quite a big gap, and then you get a less quality underside. For this sort of thing, I'd probably go 0.1, 0.15. You can change this number to whatever you want, like 0.15, 0.17 I often use, is a good compromise of trying to get as close as possible. Well, the idea is to get as close as possible to give it the best support, but without it sticking too hard, because then the harder it sticks, the harder it is to break off and trim, post-processing to clean it up. So this is so tiny, so I could probably get away with even less, like 0.12 or something. There's also, I'll show you the 3 different support styles that this slicer has, which is grid, snug, and organic. Grid's kind of the old school one. Grid and snug are similar. The snug is a bit more compact, doesn't use as much material, doesn't use excess around sort of outside of the object. It's just a bit more refined, I guess. So snug's pretty common that I use, and organic's also pretty common that I use. So that was snug as the default for this profile. But I'll show you organic because that's really interesting. So switch over to organic and go back to the plater and reslice. So now you see we've got these organic tree looking type supports. So instead of it being a box structure, like sort of square box structure, it's more like a organic tree, literally as per the name, organic, which is often uses a lot less material, and it can also get to places by bending around the object, your actual component. It can get to places that the support from the build plate only can't get to. There is a support everywhere which actually can build supports on top of your component, which then makes it a bit harder to take them off and may compromise the cosmetic look of the surface afterwards. But generally I'd try and use supports on the build plate only, and the tree supports can get to some areas. This one doesn't matter because it's simple to get to, but it can actually wind itself around the shape and back in a bit. It can go to a certain angle, and then support an otherwise not easily supportable area of your component. And it does seem to give a lot of cases, it seems to give a nicer finish, just for whatever reason, I'm not sure, but it does support well. So that's a really good option to use, and it can often use a lot less material, because you can see here, it's just got one little base point, and it sort of branches out. So you've got like that amount of material rather than a full box structure. So that's pretty cool. Let's go with that. So we've got it well sort of foundation supported, got a brim, we've got our support structure, and we've got our overhang supported where needed. Well, maybe not, but good demonstration. we've got a good distribution of strength through the whole component, or as much as we can for this current design. Cool. So at this point I go, right, I want to print. Let's do a first print. So I go export G-code, and then you just save your G-code file. So you won't be able to see this, but that folder structure I showed you before had the Blender STL slicer. Well, actually, let's save this first because I haven't saved this yet. So you go File, Save Project As, and then you can save it into your 3_STL folder. It'll default to the name of your imported object, or you can name it whatever you want, of course, but usually the default's pretty good. The file name -shock tower. So this saves a .3mf file. So 3mf is a reasonably open source standard for slicer. I found you can open the .3mf files in different slicers. So if I distribute a .3mf file to other people, they can open it in a different slicer. But I have found that it's not 100% one for one. So you might get some settings, but you might not get 100% of my settings. So it's a bit hit and miss. So it's not totally robust in that way. If you opened it in Prusa Slicer, you would get it absolutely perfect as is, and every single setting I've done, you would get that shown in your slicer for this file. So yeah, the 3mf files are really cool because it gives you all of this slicing configuration, saves it all, and you can distribute that to customers or friends or whatever you need to do. Yeah, so I've saved that now, and now I'll export. And then, so that was in my slicer folder. Now I'm going to save my G-code into my G-code folder. Cool. Yep. So that gives you your dot, in this case, .bg code file, which is the binary version that Prusa uses currently. And then the next step is to print it. So I'll go and do that. What'll I show? You can probably see the printer in the background. We'll see how I go with editing. Hopefully you'll be able to see bits and pieces. I'll go put it on this machine, and then we'll be back when it's printed. I've now just put the print on, so that'll be buzzing away in the background. That prints take about an hour, and just over an hour for this printer, for this object. But I thought I'd just show you quickly the folder structure that I was saving the files to earlier. So here we've got like my main folder, so the Blender for 3D printing for beginners project, which is what we've been doing today. And then I've got those 5 folders, which is my sort of default structure, the way I do it. So you can sort of name them, number them, call them, structure them whatever way you want. So here's my method as an example that you can use or otherwise. So we can see, I'll just show you what we've now got as we've gone through the process. So you can see in Blender we've got the actual Blender CAD file, .blend, and its backup, blend1, the original template that I just created as my starting point. And then when we exported the STL file from there, we get the Blender for 3D printing -shocktower.stl. So that's our STL file. And then we imported that into our slicer, and we saved our slicer as the same sort of name, .3mf. There's that one. And then from the slicer we exported our G-code. And so then we get this Blender for beginners, for 3D printing for beginners, Shock Tower, and it puts us the default sort of file naming configuration, which I think it's still default in Prusa Slicer, but you can configure that as desired. It gives you some of the metrics around the structure, which is your print height, layer height, the material code, which is PC in this case, the code for the printer. So that's my Mark IV IS printer, and then the print time on 1 hour and 2 minutes. BG code, so binary G code. So the binary is just to compress. I believe it compresses it to make the file size smaller for better file transfer and performance. Moving it from your machine to the printer, and that's in the Prusa's case. That's all done. Now it's done over Wi-Fi for the current printers using the Prusa Link. It's just with the software that bundles with the slicer, I think. And yeah, there's the whole steps of configuration that in Prusa's instructions, quite straightforward. Nothing too super flashy. It's just the basics of configuring it on your network so that it can access your local Wi-Fi network. And then each printer has an IP address, so the Prusa Link lets you literally go to that IP address, and it gives you a little basic interface where you can transfer the files, and also lets you see what's currently printing. Let's show you that. So here is the Prusa Link. So it runs in the browser. You just go to the IP address once you've configured it all. And then, this is kind of the interface. So it gives you the dashboard is what's currently printing. So you can see there we've got our new little shock tower is the currently printing file. Just kicked off, so it's still just warming up. And if I go to storage, then that's like your folder structure where you can drag and drop the files from your local file system, and you drop it into the storage. So you can see here I create a miscellaneous folder which I've got a whole bunch of previous prints, and then I create folders in here for my different projects, so sort of segregates them here a little bit, just basic. I found it's better not to have too many subfolders, just have one folder per project, and then I have a miscellaneous folder to sort of catch all for other bits and pieces. So we can see here, this is the file that we just uploaded. And then back to the dashboard, and it's just started doing its warm-up routine. And off it goes. So we'll be back here in about an hour and 2 minutes. So. So there it is, all printed. So disconnect the supports, and the base bit, and the brim. So the rest of the edge of the brim there and the corners, I'll just trim off with a scalpel and give it a quick sand. So yeah, there you go. I'm pretty much going to wrap up this video with that. So that's the whole end-to-end process. We've gone right from downloading and installing Blender, setting up the environment the way I set it up, the sort of mindset and a bit of the approach and concepts around structuring the design, and also the specific features that I use within Blender to do this. A tiny little micro portion in the edge of Blender to do something basic. And then we've sort of debugged a few mistakes and little issues and behaviors of it. And then we've exported the STL, opened that up in the slicer, manipulated the object, doing all the slicing configuration, and then export to G-code, send that off to the printer. It did its job beautifully, as always. And then we have an object. Where's the original? Got to compare it to the original. So there's, wait a minute, this is the original. And then we've got the print. So this is where I go and so measure it all and double check and see how it compares. If there's errors or bits I want to change, then go through that process again, of course, until happy. Usually I'd print this in like the first print especially, I'd print in a cheaper material like the PLA or PETG. I did this one in PC Blend because it's small and shows you the sort of final product that I do. But yeah, neither here nor there. So then I would clean up the part, measure it, check the holes, and then go and install it into the car to make sure it fits and integrates. And as I said, you just keep going through that iterative process of tweaking the design, improving it, fixing things, until you get to a point where you're happy with the result and it's fit for purpose. And off it goes down the track or wherever. So very cool. Still freaks me out, blows my mind sometimes, just the whole process that you can have a concept, you can take it from inside your brain or from an existing part, and you can create something new sort of from nothing, so to speak, which is pretty awesome, especially in hobbies such as RC racing and similar things to that, where you can't buy certain parts and you want to think up your own designs and components and make them exist. And this is such a cool way that we can do as a consumer at a pretty reasonable or pretty low cost. So there you go. I'll wrap up this video there. Thank you so much for watching. I'd be very keen to hear your feedback of, do you want me to go into more detail in certain areas? Because we've done a bit of a high, medium level run through from end to end. There's heaps of specific parts which I would have glossed over or not even shown. If you're interested in them, please leave a comment or give me a message, and we'll look at doing future videos to try and to cover different topics, different aspects, and it's all good. Thank you so much. See you in the next one. Bye.